y equals to mx plus c. There was a bit of doubt on how those things came about and how did the manipulation of those things. So this lesson today it is going to give you a brief of introduction about all those aspects and to manipulate how to manipulate this formula. So for us to do that, we are going to study a heading, a subheading called gradient descent. Yes, we are going to study this gradient descent. So on this gradient descent, if I need to run out this program, we are going to see on the introduction to gradient descent. So I ask a question, what is gradient descent? Uh, you answer me, what is gradient descent? In my own light and with all academia, they say that gradient descent is an optimization algorithm used to minimize function, especially in machine learning and statistics. The goal is to find the minimum value of the function, which often correspond to the best fit parameters in a model. Okay. Yes. After answering this the definition of gradient descent, yes, I know that your next question will be how does the gradient descent work? Okay, let's run this program. Okay, I say that how gradient descent work. Okay, I say objective function. Are we there? The function the function you want to minimize. That means you wanted to minimize a given function. Okay, in the machine learning, this is often the cause of the loss function that measure the difference between the predicted value and the actual value. Last time we calculated the difference between the predicted value and the actual value. That was what the loss function. So then the secondly, the parameters. Okay, you want to measure the parameters. So the variable of the function that are adjusted to minimize the objective function. For instance, the linear regression. These are the slope, the m and the y-intercept. Those are the two parameters. We have the m and the y-intercept. The m is the slope and the y-intercept. The c is the intercept. The slope is the m. Are we there? Then now, when we have now learning rate, we see that learning rate is the hyperparameter that control the size of the step taken toward the minimum to large. A learning rate may cause overshooting, while too small rate can lead to slow converge. So learning rate is a given parameter that you have to give. You can decide that to give your learning rate to be 0.01. But now in this lesson, you are going to see how we are going to give our learning rate and the different how it's going to affect our work. Okay. Then we have now the gradient descent. Gradient descent, the derivative of the objective function with respect to what the parameters. It indicates the direction and the rate of stiffness. Ascend the gradient descent. Use this to update the parameter to opposite the direction downhill. So for gradient descent, now you move from the highest level to the smallest. Move from the highest level to the smallest. Move from the highest as downhill. Move gradual process. Okay. So we are going to see about that. Let us move. Then I know that you will ask a question that say how many type of gradient descent do we have? Those are the next questions that I know that you will ask. So I've written this code for us to know about this. Let us run the code. When we run the code, we are going to learn that we have three types of gradient descent. We have what? The batch gradient descent. We have mini batch gradient descent. We have stochastic gradient descent. Okay, now let us define each. We said what for batch gradient descent, update the model parameters using the average gradient over the entire data set. Okay, take note about the entire data set. It provides the stable conversion, but can be slow for large data set. And it used all the data set in order to run the program. But now look at mini batch gradient descent. it update the model parameter using what? A subset, a mini batch of the data set, a subset. Take note about that. A balance between the efficiency of the stochastic gradient descent and the stability of the batch gradient. So we have mentioned a word about stochastic gradient descent. Okay, now let us look at now stochastic gradient descent. What is stochastic gradient descent all about? Now, I say that it updates the model parameters using a single data point at a time. It can be fast and more memory efficient for large data set, but it can have a variant in update. So at this point now on stochastic gradient descent, it does not take all the data set, but now it now take out in a move now from point to point, right? If I can call it in a good terms, that it randomly choose each it choose it does not we don't take all, but it randomly choose various data, then it run the program. Okay, so if now we look at our let us run this program. Yes, this diagram is showing us what the last information that we had in our last class. If you haven't studied the last class on linear regression, again we look for what the sale, the sale, that's the advertisement using the TV and the sale. So we wanted to predict now the price. If really when we do more advertisement, are we going to gain in the company or are we going to lose? So we did now there were a lot of advertisement, but this one now we use now one data set. Okay, so at this point, if you look at, we have the predicted line, this red line is a predicted line, but our data there we have what was, there are 10 of them in numbers, there are 10 of them. So we have x, we have what x1 y1, x2 y2, x3 y3, x4 right up to x10 y10. So the n is a number of 10. Are we together? So at this point now, if now this blue line need to lie on this red line, it obviously shown that our predicted line is perfect. But now the blue line now does not lie now on the red line, but it's beside. So now the cost function, or the loss function now, it is a difference between this blue line and this red line. Let me repeat it. The loss function is the difference between the red line and the blue line. So now that is the reason that we are going now to use now some statistics formula in order now to calculate it now. Okay. As I've mentioned about statistical formula for us to calculate, you ask now say what is a formula? That is the next question that I expect from you. Let's say what is a formula? Okay, now let us run this program. These are the formula. This is the formula. Are we there? Now this formula now is telling us about what? About the mean square error. Now this is what the real value. This is what the predicted value. This is the predicted value. This is the real value. On this is the predicted value. The predicted value is what? The value, the red line. The real value is at the point of the blue line. So we intended to predict this red line, but we predict at the point of this. So we need now to look at how we are going now to work things out. That okay, if we need to look what are the statistics term that we are going to use now in order to work all the sum of these 10, because we have 10 elements, there are 10 of them here. So how are we going to work things out that it is going to give us what we need? So we give now n is the number of data points, y is represent the observed value, and y is yi and y hat represent what the predicted value. For more explanation, I have written this code. Now this code now give us now our various values. Okay, I call this new value equals to old value minus the step size. And the step size is the learning rate multiplied by the slope. The slope can be the gradient. Okay. Okay, now the slope is the derivative. Learning rate, we can put our learning rate to be 0.001. That's always like a standard of this, but at this point you will see that the learning rate we can reduce it more and we can increase it more. So it depends on what we are working out. Okay. So at this now we have now this is our line. This is our function y equals to mx plus c. So the mean square error MSE is equals to this. This is the formula. So at this point, we need now to write some code. We write some code that is going now to, in each line of that function, is going now to print. So we are going to print now various iteration, line 1, line 2, and it depends on the various iteration that we are going to give. We can give about, let's say, 100. That means we're going to print it 100 times. And in each line, when we feed n, what is it going to give us? And when we feed c, we feed c, when c is equal to this, when m is equal to this, what will be y? Now, in the second line, when c is this, when m is this, what will be this? So we are going to do that 100 times. So for us to do that in mathematical expression, it will take us a lot of time. So with machine learning, it is very easy. You just write some various line of code in order to do that. Okay, so now these are the line of code that we have written. This y represent the y predicted, and this m represent the m here. This is the multiplication sign that is multiplying by xi plus c. This is a c. Now we say cost. This is MSE is a cost. The mean square error is a cost function. So this is the formula of the cost function. M1 over n, this is the various formula. Using what? The full data set for cost function. Then the m gradient. This is to calculate the gradient. We have the m gradient, that's the gradient of m, gradient of c. We have what? The learning rate of m and the learning rate of c. Are we there? Yes, for more explanation, I have written this code. Now, this code now is telling us that we have import numpy as np, we import matplot because we wanted to plot some graph. Okay. So now at this point, we say function to perform. We wanted to start with what? Batch gradient descent. So now we define the batch gradient descent, x and y. Then the number of iteration, we give it to 100. Our learning rate, as we said it ahead, our learning rate, I have placed my learning rate to be 0.001. Okay, so the x now np array, we change the number array to what? We change it to number array, right? So at this point now, when we change it to number array, yes, when we do that, we have now this other line of code that, okay, this one, ensure the shape of x and y match. So we write a code now that if the length is equals to x or equals to the length y, the length it should match, the length of x should be matched with the length of y. If it is not equals to this, if it's not equals to, we do what? Raise the value error. Raise error. X and y do not match. This is what, if it is not equals to, this statement is going to run. This error statement. But now, if this is equals, okay, now we have what? We initiate the slope m equals to 0. We initiate what? The intercept c equals to 0. The number of data point n, length of x. So our number of data point is 10. N equals to 10. If you look at from this diagram, this is nx x10 of y10. This is number 10. Number 1 started from here right up to the number 10. So this number of blue points are 10 of them. So show that our data number of data point is 10. Okay. Yes. Then when we have that now, we have to list to store the value of m and c and the cost of each iteration. So we store the value of m value, we store the value of c value, and we store the value of the cost value. Okay. Yes. After doing that, we then now write now our for loop. We say that word for I. We write our for loop, bring it back. Voila. We write our for loop for I in the range of iteration. Y predict is equals to what? This is our formula. We calculate the predicted of y value. Are we there? So we mention the formula over there with the cost. So we calculate the cost function, m gradient. We calculate the gradient for m, c gradient. We calculate the gradient for c. Are we there? Then m learning rate times m gradient. We update the m using the learning rate, c learning rate times the c gradient. We update using the learning rate. Are we there? We update c, that we update c using the learning rate, update m using the learning rate. Okay. After that, what are we going to do? After that, we have to store the current value of m, c, and the cost. So we have to store this value. So for us to store this value, we are going to call append. We say m value dot append of m, right? Store of m, c value append of c. We call again cost value append of cost. So if you haven't watched that's our Python lesson, please you have to go back and watch our Python lesson, because we learned about I taught about this append. That's in the lesson right up to lesson from lesson 8, 9, 10, and 11. Try to watch that lesson. You are going to see about append. Okay. Okay, now let's move forward. After that, we have to print the iteration. Okay. So at these 4 decimal places, 4 decimal places, 4 decimal places. So C in 4 decimal places, M in 4 decimal places, the cost in 4 decimal places. They will return the M, C, and M value, C value, cost value, return the final history. Okay. So now, this is what after return. Now example usage. We say okay, if our x, I've placed this formula for us to use it. If our x is this our data set, y is this. This is the same data that we use for the sale price versus TV. Are we there? So if our x is this and our y is this, we say that what we should try m and c value, cost value, batch gradient descent, x, y. We want to print the final equation of what of y is this plus c 2f, print the final linear equation. Are we there? Accept the value error as e. Now we have to print if there's value error, print the e, print the error message if the value error erased. Right? If the value error erased, you have to print the error message. That is the reason that we place this. Now later now we have to do what? We have to plot the value. Iteration, the list ranging from what 1 to 101. Yes. Then we plot the figure size 12 and 18. We have x and y, right? Then we plot for m value. Plot the subplot of 3, 1, and 1. Plot the iteration of the m value label, m and the color blue. Plot the x level. If this other one, you have to go and learn my pandas lesson, that's lesson 34 right up to 35. Okay, pandas lesson. Then plot the x level iteration. So we have all this. So we have to plot the m value. So move again ahead. So we plot the m value, we plot the c value, we plot the cos value. Okay, so those are the three values that we are plotting: the m value, the c value, the cos value. So when we must have done that, we have to run our program. Yes, after we run the program, now let us look now. Okay, now we have run the program. This is our result. We have iteration m, c, and cos. Are we there? M, C, and cos. So now, if you look at it very well, yes, we say M is what? The slope. This is the slope. C is the intercept. This is the cos function. The cos function. This is the error. Are we the cos function? This is the error. Now, at this point now, this cos function is the error. The error is this distance. Let me draw our attention. The distance between what? The predicted value and what? This other one. Are we there? This is what the predicted value, and this is now the, so now this distance between here is a cos function, the error. So let's come back. So at this point, if you look at from the first iteration, the cos function is high. We have 190, 169. But now, when now you are going down, the second iteration, it reduced to 91. The third iteration, it reduced to 56. The fourth reduced to 41. It starts reduces as it is going down, reduces. If you look at it very well, at the point where we have at the 10th iteration, we have 30. Now you start having that 29, 29, 29, 29, right up to going downwards. It's showing that what? It ends at that point of 29, at the point of 29, there is no changes again, there is no changes again. There is no change in 29, 29, all downward. So if we look at our graph, we are going to see it very well. Now our graph now is telling us what? About what? The iteration over what? The m value. Okay. So now, if you look at from 0, we have 0, from 0 right up to this point, right up to 10. That is where we have change. But when it arrives at 10, the line remains the same. For m value versus iteration. Also, when now you look at the iteration versus the c value, the intercept, it started what from here. At this point, it moved right up to, this is a maximum 0.06, and what we have 100. So if you look at here, that is what, this is what the m value, m, this m value, you have 0.09, this is 0.09, 0.09, m value 0.09, this is a maximum 0.09, the maximum. Are we there? Then now, this is the m value, the maximum 0.09, and it is what? Mapping with what? The number, the maximum iteration is 100. So at that point, it moves right up to, there's no change at that point. So it's showing that if you also look at the c value, its maximum is 0.06, the c value is 0.061. Are we there? So this is a c value 0.061. The maximum is 100 iteration. Then now the cos value, for the cos value against the iteration, what do we have? We realize that at the level, it started what? At a given point, it started going down. It arrived at the point where we have that from 10, it become constant, 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 right up to the end. That was a reason, that was a reason, if you look at this, let me scroll down. If you look at this is iteration 10. Iteration 10, we have 30. When it started going down 29, it remained the same right up to iteration what? Iteration 100. Are we together? Yes. Let us move forward. I will not explain more on the stochastic gradient descent because they are mostly likely the same. They are just a slight changes. So I'm going to paste the code and I explain less, then we continue. Before we continue on that, we have to first of all let us work on this function mini bash gradient descent. Then the stochastic gradient descent will be the last one. So I have just now placed the code on mini bash gradient descent because I don't want us to waste a lot of time because this lesson has taken us time. Okay, so I just need to highlight now the difference on the first one and the second, the bash gradient descent and the mini bash gradient descent. So on now mini bash gradient descent, what is happening? Everything, this first line is the same. Now what do we do? Ensure the shape of X match. This one is also the same. We initiate this is the same. Now list store the value of is the same. We don't have any problem. Now at this point, this is where we did some a little bit of mathematics in the mini bash gradient descent. That we now happen to do what we shuffle the indices. Okay, we NP we random permanent we random now pick some values. Are we there? We random now pick some values. So that is a different because the code now change here. And when the code change here, it obviously now showing that the format now it changed a bit, but it does not mean that at this point it does not mean that you have a different result. The result on the first one is supposed to be the same or slightly different, but all of them supposed to be the same. Okay, so when we run this program, we have run the mini bash gradient descent. All the formula remain the same with the first one. That's why this second one we don't explain too much. So compare the first, this one, the line. What is this line? This line, this equation, final equation of the line is y equals to 0.09x plus 0.01. Okay, now let's look about this one also, this line. What is this line? Let me scroll down this very fast. Okay, its line is 0.09 plus 0.03. So the slightly different is at the point of this, but it's slightly the same. Okay. Now there are, if you look at now other mini bash now, it's showing that at the point of our m value we have a rough line. It's a big rough. But while on the bash gradient descent, it was smooth. Take note about that. Then also, if you look at the point of the cost value versus the iteration, we realize that there is a fluctuation upward, 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 upward. Are we there? But on the bash gradient descent, this fluctuation is not there. Yes, let's move on stochastic gradient descent. So I've already write all the code, so we don't have time to be explaining again because we have already explained that. That is the reason that we explained the first code very well, such that because before doing this, I've already rerun the code to see that the code is free because there is no room for error or there is no time again for us to debug here. Okay, so now this one now is stochastic gradient descent. Are we there? We use our number of iteration is 100. Learning rate, the same learning rate. Are we together? Then this one we are going now to see if we alter this learning rate, how is it going to look like now like this. So at this point now, This is where we have a changes. We randomly pick an index, okay? We randomly pick an index between 0 and n. We randomly pick an index between 0 and n. So but the other one, it take everything, but this one randomly pick the index. So if we run this program, we are going to realize that, look at, it started from 139, 136, 79, goes down 30, 30, 29, 30, 29. You see, it goes up, goes down, goes up, goes down, goes up, goes down. While in the other, the first part on batch gradient descent, as when it arrives at a point, it just go down direct. It does not go down again. It does not go up. But on stochastic gradient descent, it will go up, go down, go up, go down. That is why you are seeing 30, 29, 30, 29, and that is how the graph also will look like. The graph will be dancing. The graph will be dancing. So as we are going down, you will see this is the graph. Look at, the graph is dancing. Because why? It is going up, down, up, down, up, down. That is stochastic gradient descent. Also, a mini batch also has the same, but the stochastic gradient descent is more of that. So if you look at even his graph on C value, is also fluctuating. Then now the real one also is this. If you look at on cost value, at the point of 10, that is when it's having that issue also. At the point of 10, it starts fluctuate. It starts fluctuate. It starts fluctuate. Okay. Hello. Thanks for watching. If you find this video useful, may you give a thumb up, you like and share the video. See you in the next video. Okay. Take care. Make sure you have a comment below. If there's anything that you need my help, you let me know. That is the reason that I'm here. Okay. Bye bye. Thank you.